Greetings, welcome to lecture number 31 on basic circuit theory. I am Razavi. Today we will continue to look at the lossy LC tank, which we will now call the parallel RLC circuit, and analyze some of its other properties. And that prepares us to go to the case of the driven circuit, meaning when the circuit has an input. So far, we have only examined the response of the circuit to an initial condition, and we have found its natural response. But now we can look at this response to an input. But before we go there, let's take a look at what we have discovered so far about the circuit. We saw that in the presence of this resistance, the output voltage and these currents all have to go to zero eventually, because the energy stored in this capacitor initially is all dissipated by this resistor. So we found the characteristic equation, and we found the roots of that, and we came up with this expression here. And we decided that depending on whether this term under the square root is positive, zero, or negative, we have three cases. We have the overdamped response, the critically damped response, and the underdamped response. So when we looked at this output voltage as a function of time, we saw that if R1 is small enough, which would be the case, this blue case, so if this resistor is small enough, we allow almost no oscillation. So you can see that Vout just comes down, there is a dip, but then it settles, right? It doesn't go haywire, so to speak. If we have R1 equal to this value, 1/2 of square root of L1 over C1, then it's critically damped, and that means that the response settles fastest. So that's this red waveform here, and still it has a dip, but then it settles smoothly to its final value. On the other hand, if R1 is large enough, meaning greater than this value, then the circuit exhibits some oscillatory behavior. You can see that now the output voltage goes up and down periodically before it dies away. So we see that if this resistor is not very large, if it's small enough, below this limit here, so in this case, we have an overdamped response. If it's equal to that limit, we have a critically damped response. And if it's large enough, we have an underdamped response. So, which one of these responses is desirable? Well, it depends on what we're trying to do. Oftentimes, if we are building a system and we would like the system to settle to some final value, we would like it to be well behaved. So we would opt for this red waveform and try to design the system so that it's critically damped. But there are some other cases where that's not true, and we'll see an example today. Okay, so let's go over some other properties of this circuit. So other properties of a parallel RLC circuit. So first I wanted to make sure that in our analogy with the pendulum, we are not confused about these three cases. So when we looked at the pendulum response, we saw that when we release it, it goes up and down, it swings, and it decays due to the frictions that we have in the system. But in the RLC circuit, we see that only in one case do we really see this type of oscillatory decaying response, right? So if you remember from these plots, you see that only for the green plot, when this condition holds, do we have this type of swing before it dies. For the critically damped, and for the overdamped case, we have only a slight undershoot, if you will, meaning that we go below zero a little bit and then we settle, right? How could I make this pendulum behave like that, approximately speaking? So what I would like to do is for this pendulum to just come down like this, go past the vertical position a little bit, and then just gradually come back to vertical position, right? That's what it means to have this blue waveform. The blue waveform wants to reach its final value, which would be here, but it has a bit of undershoot and then comes back slowly to its final value. So that would be possible if we immerse this pendulum in some sort of liquid with a great deal of friction, a very thick liquid, like in a viscous type of oil or in honey maybe, right? So when we release it, there's so much friction that it just loses all of its energy in the form of heat, and by the time it gets here, it has very little kinetic energy left. So it just goes a little bit past that point and then gradually comes back to that point. So very roughly speaking, the pendulum could respond like this blue waveform if it were immersed in something very lossy, meaning with a great deal of friction. So that's one point that I wanted to mention in conjunction with the pendulum. But there are some other interesting things that we should look at. Okay, so we say, what happens to the response as R1 goes from infinity to very small values. Okay, so we have our tank. Here's what we have, and we have a resistor R1. We are looking at this voltage. Same story as before, and I designed the circuit with different values of R1 while keeping the capacitance and the inductance constant. And I would like to see how V out changes as a function of time in these different cases. Okay, so let's do that. Qualitatively speaking, we should be comfortable constructing these plots. All right, so we start with when these are all V out as a function of time. We start with a value of infinity for R1. All right, so R1 is not here, it's open. So we have an ideal LC tank, and we saw that with an initial condition, the circuit just keeps oscillating forever, right? Okay, so that would start with V0 here, and it would oscillate forever. Okay, so that's for the case of R1 equals infinity. All right, now let's go ahead and reduce R1 from infinity, so now it's finite, some amount. So what we see is that in that case, so V out of R1 is less than infinity, but large. Now, of course, the term large has to be quantified, but that's okay. So if R1 is large enough, what happens is that we gradually lose the energy of the system over time. So we have a sinusoid, a cosine, but it decays very slowly. So it has some sort of envelope like this, and the envelope is a very slow exponential. So it's going to go like this, and gradually it decays. Okay. Now we keep reducing R1. So if R1 is reduced more, what we expect is that this decay becomes faster. So before we reach that threshold value, so remember that R1, depending on this value of R1 and how it compares with this quantity, we can have one of those three cases, right? So if R1 is small enough, meaning this, we have overdamped. If R1 is large enough, like this, we have underdamped, and if it's equal, it's critically damped. So we started from a large R1, and we keep decreasing it. So this is underdamped, right? And if it's R1 is still greater than this value, it's still underdamped, but because R1 is smaller and smaller, the response decays quickly. So now here the exponential will decay quickly, and that means that the response just quickly dies, right? So this is R1 somewhat large, and by that we mean it's still larger than and still larger than 1 over root 1 over 2 L1 over C1. So these are both underdamped cases. Here is a larger resistor, here is smaller resistor. Okay, and then what happens if we keep reducing R1 further? Well, eventually we reach this limit of 1/2 over root of L1 over C1, so we reach the critically damped situation. So I'll draw that here. So we say V out as a function of time, and we are right on the edge. So R1 is 1/2 of root L1 over C1. So now, as we saw before, V out has just a dip, but it settles pretty quickly. So V out comes down, has a little dip below 0, and then it settles. Okay, so that's critically damped response. And then finally, if I pick R out to be even smaller, so now R1 is less than 1/2 of L1 over C1, then we have an overdamped response. So it will come down more like this. Will come down and it will slowly reach 0. All right? So depending on how we play with a value of R1 compared to 1/2 of square root of L1 over C1, we can get these different responses. Okay, so as I said, in many systems, we care about how fast we reach this final value, how fast we reach our destination. This could be mechanical systems, could be electrical systems, social systems, many different systems. In those cases, we would like to approach the critically damped response. So we try to choose the values such that we can reach the final value in as short a time as possible. But there are some cases where actually we don't want to do that. And here's an example of a case where we want to do something different. So let me give you a quick example to show you how this works. Okay. There's a type of circuit called an oscillator. So oscillator. And we don't know what it is, what it does, but at a very high level, an oscillator generates a periodic output. That periodic output could be a sine, a cosine, or it could be a square wave, depending what we want. But it's just a box, and the output is periodic. Okay, so for example, let's say it's supposed to be like this, right, as a function of time. So we would like to build an oscillator. We have oscillators everywhere. In any electronic equipment today, in any type of device that you have, from mobile devices to computing devices, etc., we have many, many different types of oscillators. For example, the clock that drives the circuits in your laptop or your mobile device is a periodic signal, and that is produced by an oscillator. Okay, so how do I build an oscillator if I have this type of circuit? We see that this circuit almost oscillates indefinitely, but not quite, because there is always some loss in the system. So if you just give the initial condition to the capacitor, it won't hold up, right? It will just decay and die. But I don't want it to die. I want it to be periodic forever. So how do I do that? So there's a very interesting technique that allows us to do this, and the technique is as follows. So this oscillator is realized in some cases like this. We have a capacitor, we have an inductor. So we buy a capacitor, we buy an inductor, we hook them up. That's our tank. Unfortunately, this tank is lossy, however you build it. So we will use the resistor here to model the loss. It's not that we deliberately add that resistor, it's just that this resistor is actually part of the imperfections of this tank that we have built. All right, so here's the problem, right? The problem is that this resistor causes this oscillation to die away. If this resistor were infinite, we would be okay. But because not infinite, we are losing the oscillation. So what I will do is I will take some sort of circuit, So we call this electronic circuit. And this is something that we do not discuss in this course, but we can easily build that. We build an electronic circuit. And that circuit has only 2 wires coming out of it, right? So I put this in a box and I think of it as just a resistance. And what I do is I design this electronic circuit such that the resistance created between these 2 wires by the circuit is a negative value. Strange but true. We can create circuits whose input resistance is negative. So if this is R1, I will build this such that if I sit here and measure the resistance between these 2 wires from that circuit, it's minus R1. So do you see now what happens? So I have R1 here and I have minus R1 here, and they're in parallel, right? Because they share these 2 wires. So the equivalent resistance that the tank sees now is R1 resulting from its own loss and minus R1 provided by the circuit. So that would be R1 times minus R1 divided by R1 minus R1. Right? And this goes towards minus infinity. And what do we call an infinite resistance? Call it an open circuit, right? So it's an open circuit. And because it's an open circuit, it means that this and this together act as an open circuit, so they don't draw any current from this tank, so the tank can happily oscillate forever, right? As if you had an ideal tank, because we're looking for an effective resistance of infinity. So it's a very common approach that we use to build these types of oscillators using inductors and capacitors. Okay, it's a fascinating idea. All right, so that's one other point that I wanted to mention about the parallel lossy circuit. Let's see. Let's talk about oscillators and their application in real life. We talked a little about how we can create an oscillatory waveform when we talked about RLC circuits. We saw that if we have an ideal inductor and an ideal capacitor forming a parallel tank, and the capacitor has an initial condition, and we let the system go, we do generate a periodic waveform. And this periodic waveform has a certain frequency given by 1 over square root of L1 C1. But then we saw that in reality, there are some resistive losses in these components that do not allow this waveform to run indefinitely. So in practice, if we build that circuit, there is some resistive loss, which we just model for simplicity by a parallel resistance. And as a result of this heat dissipation in this resistance, we see that the waveform decays and eventually dies away. So then we thought, okay, maybe to allow this oscillation to continue, we should try to cancel the effect of this resistance. And we said, okay, maybe there's some sort of circuit that can have a negative resistance, as we saw before, and this negative resistance is equal to minus RP. So if I just replace this box, this is some sort of active circuit which we don't know, we replace this box with its equivalent resistance of minus RP, then we saw that minus RP and plus RP give us a net result that's infinity, so it's like an open circuit, and that means that the tank can now oscillate forever. In a sense, what's happening is that this resistance dissipates some of the energy from the tank, like so, but this circuit replenishes that energy, brings that energy into the circuit in every cycle, so that these two cancel each other and the circuit can go on indefinitely. Now, this circuit can actually be realized by means of transistors and so on. We haven't seen those in this course, but here's a very common technique where we have our tank. As you can see, I have just rotated it by 90 degrees, this tank here, and then we have this circuit here, consisting of some devices that we are not familiar with. And the job of this circuit is to create a negative resistance such that that negative resistance cancels this positive resistance. This oscillator is very common today in most wireless systems, including your Wi-Fi and Bluetooth. This type of oscillator is very likely used to create oscillatory waveforms. But we are interested in something else here. If we have an oscillator, if we know how to build an oscillator, we can also build some interesting devices. So here's an interesting situation, namely the accelerometer. We know that accelerometers are used in cars to detect sudden changes in the velocity. That's acceleration, right? In particular, if there's an accident, the velocity suddenly drops, the acceleration is a large negative number, and based on that, we can release the airbags. So inside each of these airbags, we have an accelerometer that measures the acceleration, and if it's too much, it shows that an accident has happened and it releases the airbag. So how do we build an accelerometer exactly? How do we measure acceleration? Well, we can use a capacitor for that purpose. It's actually very simple and very nice. Imagine that we have two conductive plates, like pillars, erected here on some sort of insulating substrate, insulating surface. And we know that because we have two conductive plates, there's a capacitance between these two. All right? Now imagine that one of these plates is fixed, whereas the other one can flex this way or that way. Okay, so something is different in this base to allow this to tilt this way or tilt this way. Now, if this system is accelerating inside the car, what happens? Well, this plate doesn't tilt, but this one does. So with acceleration, we see that this plate tilts this way, for example, if the car is accelerating this way. So once the plate number 2 tilts, the capacitance between these two actually changes by a small amount. You can imagine, right, that here the capacitance is given by some numbers. Here it is as if this plate has gone a little farther than before, so the capacitance decreases a little bit. So we can measure the change in this capacitance, we can measure the acceleration. How do I measure the change in the capacitance? Well, remember that the frequency of that oscillator was related to the value of the capacitance. So if I remember this equation for the frequency, so I can embed this capacitor in here. This capacitor can realize as this accelerometer. So when we accelerate, the capacitance changes. When the capacitance changes, the frequency of oscillation of this oscillator changes. And once that frequency changes, we can measure it. So if you measure the change in frequency of this oscillator, that is proportional to the acceleration that the car has. Isn't that beautiful? Okay, so we are now ready to look at the driven parallel RLC circuit, and it just means that we have an input. So let's go analyze that. So we say driven parallel RLC circuit. And that means that we have some sort of input. We could have an initial condition as well, but for simplicity, we assume there's no initial condition. So what kind of input should we choose? We can choose anything we want. We can choose a step, we can choose an impulse, etc. All right, so let's draw the circuit. Here's our circuit C1, L1, and R1. And I would like to apply an input. So I will choose a current source here, and I call it I in. Can I use a voltage source instead of a current source? Yes, but then it doesn't make a whole lot of sense if we are interested in this voltage, right? So if this voltage is the quantity of interest to me, and I apply a voltage source between these 2 points, then V out is always equal to that voltage source, whatever it is, a step or whatever we have, right? So that's not particularly interesting. This is interesting because this output voltage is created when this current passes through these 3 branches and does interesting things. That's why we don't really look at the parallel RLC circuit with the voltage applied here. We could also have some interesting properties there, but it's not particularly exciting, so we go with this topology. And in fact, this is also something that represents this type of circuit very well. Okay, so let's go ahead and find V out in terms of everything that we have here. We have no initial conditions. And remember how we wrote the differential equation for the circuit before, when we didn't have this input. We said this current plus this current plus this current must be 0, right? That's how we found the differential equation. So this time, the only difference is that this current plus this current plus this current must be equal to this current, right? It's coming into the node. That's the only difference. So let's go ahead and write that. So what we had was, so we wrote this current as V out over R1. So we had V out over R1. Then we had this current, which is 1 over L1 integral of V out dt. And then we had this current, which is C1 dV out over dt. All right, so the currents through the resistor and the inductor and the capacitor are these values. And these all have to add up to I in. So we write that as I in. Okay. All right, so that's the only difference between what we have here and what we had before. All right, now we can go ahead and again, to create a simple differential equation out of this, we can take the derivative of both sides. So we end up with something like this. I'm going to start from here. That would be the second order term. So C1 dV d squared V out over dt squared plus the derivative of this, which is 1 over R1 dV out over dt, and then the derivative of this, which would be just 1 over L1 V out, is equal to di in over dt. All right, we took the derivative of both sides with respect to time, and that's what we obtained. So we can see that this side is the same as what we had before, right? Not surprisingly. The only thing that this side is no longer 0 is equal to the derivative of the input current with respect to time. Okay, so how do we go about solving this problem? Well, what we know is that V out should have some form according to what we expected before for the natural response, right? So we had one of these 3 forms for V out. And now the only thing is that this side has changed. So depending on what I in is, of course, we will have different solutions that are added to these natural responses, right? There will be additional terms here representing what this I in is doing. So let's take a simple case where I in is a step and then see what happens. Okay, so we say I in is equal to I1 u of t. So I in is 0 before time 0 and then jumps to I1 and stays at I1 from time 0 on. And we'd like to see how to solve this equation for that case. All right, so for that, what we have to do is, let's go to the next page and see what we can do here. So I have to redraw the circuit on this page as well so that we have it available. So let's do that quickly. So we have I in, then we have our capacitor C1, inductor L1, resistor R1, and then this is V out. So we decided that C1 d squared V out over dt squared plus 1 over R1 dV out over dt plus 1 over L1 V out is equal to the derivative of the input current, and that happens to be equal to I1 delta of t, because I in is I1 u of t. All right? Okay, so that's the equation that we have, and we need to solve this equation and see what happens. Okay, so now we saw that there were 3 cases before for the natural response, and we expect that the overall solution of this equation, we still have those natural responses in it, but it may have some additional terms because this side has an impulse in it, right? Okay, so let's write this out and see. So for example, suppose case 1, an overdamped situation. So that means that, remember, our conditions were we have R1 less than 1/2 of root L1 over C1. Okay, so we have an overdamped response according to the conditions we derived before, and we have to see how we can write the output. So we'll say V out is equal to A1 e to the S1t plus A2 e to the S2t. Okay, S1 and S2 are known because they come from the characteristic equation here, right? So I can write that here quickly. So S12 is minus 1 over 2R1C1 plus minus 1 over 2, 1 over R1 squared C1 squared minus 4 over L1 C1. Right, we've seen this a number of times. So we have S1 and S2, and we have to ask ourselves, will this form suffice for V out, or do we need to add some other stuff here, right? That's what we need to figure out. Okay, so let's stay with this form for now and see if it's good enough. Maybe it is. Maybe these 2 terms tell us everything in V out. We don't need to add anything else here, right? Maybe, maybe not, so we'll just have to see. Okay, so before attempting to calculate A1 and A2, I just want to make some observations. So number 1, what we know is that V out at time 0 plus is how much? So V out at time 0 plus. So let's eyeball the circuit, knowing that we have applied a pulse of current, a step of current, so the current was 0 and then suddenly jumps to I1. And we want to see right after that step has been applied, how much is V out? Okay? All right, so this computation has to be carried out in conjunction with also the inductor current at time 0 plus. Right, so we injected a current here at time 0 plus, equal to I1. And that current can take this path, or this path, or this path. And we have to decide which one of these paths the current prefers to flow through. All right, well, we know that the current to the inductor doesn't want to change. So that's 0, because we assume that all the initial conditions are 0. So the current has to decide between C1 and R1, right? Only these 2. If it flows through R1, it generates a voltage. So V out 0 plus will be non-zero. If it flows only through C1, then there's nothing that flows through R1. So how do we decide that? Well, if this current flows through R1, it generates a voltage here at time 0 plus. But we know that the capacitor says my voltage shall not change at 0 plus because we don't have an infinite current available. So because of that, this voltage has to be 0, right? V out at 0 plus happens to be the voltage of the capacitor. That voltage is 0. So at 0 plus, that means that given that this voltage is 0, then this current is 0. And given that this current is 0 and this current is 0, all of this current has to flow through C1. So our observation number 2 is that all of I1 U of t flows through C1 at t equals 0 plus. All right, so far so good? Okay, so now let's look at time infinity also and see what's going on here. So at t equals infinity, what can we say? At t equals infinity, this current has to flow through something. This current is equal to I1. The question is, which one of these does it prefer? If you prefer this one, or this one, or this one. All right, so we have to think about that for a moment. All right, so what we expect is that at time infinity, all of the quantities in the circuit have reached constant values. Some of them have reached 0, some of them have reached a finite value, but they're all constant. So we use that notion to figure out how the capacitor and the inductor behave at time infinity. So we write all currents and V out are constant. So if the voltage across the capacitor is constant, the current through it is 0, right? CdV over dt. So that means cap current is 0. Okay, so at time infinity, this current is coming in, it cannot go through the cap. The cap is an open circuit, remember that? Okay, how about the inductor? At time infinity, the current through the inductor is constant. So the voltage across the inductor is 0. So that inductor acts as a short circuit. So we say inductor voltage is 0. Right? We've seen this in the past, that when nothing is changing, the capacitor acts as an open circuit and the inductor as a short circuit. So now if I put these all together, what can I say about where In should flow through? It cannot flow through this. That's open. Can it flow through R1? No, because this voltage is forced to be 0 by L1, right? The inductor voltage is 0. If the inductor voltage is 0, the resistor voltage is 0. That means no current can flow through the resistor. So that means that the value of I in, which is I1 at time infinity, has to entirely flow through L1. So the important result here is that all of I in U of I in, which is I1 U of t, flows through L1. All right? So in summary, what has happened is that right after the switching event, when we apply the step, all the current flows to the capacitor because the capacitor acts as a short circuit, and that's the preferable path for the current. And at time infinity, all of the current flows through the inductor because the inductor acts as a short circuit when nothing is changing, so the current prefers to flow through that. All right, so those are the two extreme cases. Okay, so based on these, let's go ahead and for the case of overdamped response, try to sketch these voltages and currents just to get a feel for what's going on, right, before we write equations. Okay, so V out, the output voltage as a function of time. We want to see how much that is. So we said that 0 plus is 0, right? We said that time infinity is also 0. So over here it's 0. And then over here it goes to 0. And in between it does something, right? So it's probably something like this. We don't exactly know, but it has some sort of shape like that. All right. Okay. What can I say about the current through the inductors? So again, let's try to sketch that as a function of time and see. So the current through the inductor, meaning this current right here, right? The current that's going down through the inductor. So we decided that time 0 plus the current is 0. At time infinity, it carries all of I in. So it looks like this. Starts from 0, and then it reaches a value of I1 at time infinity. Okay, so we go like this. We say I1, and it goes like this. Now, again, we don't exactly know how it gets there. It could be that it goes up and down before it reaches there or not. If it's an overdamped response, it probably goes like that, right? Okay, so that's the inductor current. So let's eyeball these results for a moment and make sure that they all make sense. I want to perform the same analysis as I did last time for the current at the inductor vis-a-vis the voltage that you have across the inductor. So what we know is that the current through the inductor is equal to 1 over the inductance value, integral of the voltage across it, right? So what I have to make sure is that this response is an integral, it can be the integral of this. There's no inconsistency as we saw last time. Okay, so what this says is that the current through the inductor is 0 up to here. If I integrate this, I get 0, no problem. If I integrate this and I go, the area under this keeps increasing and increasing and increasing monotonically, and this current is also increasing and increasing monotonically. So there's no inconsistency here. So these two can be the responses of the system in the case of an overdamped situation, right? When we have something like this. All right, so in other words, V out doesn't have to go dip below and come back in the case of overdamped response. All right, but one more quantity that we have to think about is the current through the capacitor, and that becomes much more interesting. So let's go ahead and mark this current, and I would like to plot the current through the capacitor as well. So we'll call this I cap. All right. Now, so this is an interesting situation. I will give you 1 minute to think about it and see how we can sketch I cap given that we have these results so far. All right, I'll give you one minute. Okay, so what do you think about the behavior of I cap? Well, we know that right after time 0, at time 0 plus, the capacitor carries all of this current, right? It acts as the short circuit. So we decided that all of this current has to flow through C1. Okay, so the current is up here. And then what happens? Well, as time goes by, we know that eventually all of this current has to end up in L1, so C1 has no current at time infinity, as we discussed here, right? So cap current is 0. Okay, so it has to go towards 0. The question is, does it just go like this, towards 0, or not? So we have to think about that carefully. All right? Okay, so what I will do is I will say, well, I cap is given by a simple equation, right? So I cap, the current through this capacitor is C dV over dt. The voltage is V out, so it's just C1 dV out over dt. So what I have shown here has to agree with the derivative of what I have shown here. So the question is, does it? Okay, so here, see that derivative is positive, and the current is positive. Okay, no problem there. Here, derivative is 0. The current is not 0. So that's not correct. Here, the derivative is negative. The current is not negative. So that's not correct. So we have to sketch this current such that it agrees with the derivative of V out. Okay, so that shouldn't be that hard. So we'll say this is no good, right? And we'll draw it using a different color. Green would be nice. So what we know that the derivative of this is positive. So here's positive. Then right here, the derivative is 0. So at that point, the current has to go to 0, right? C dV over dt. So this current comes to 0. Then it goes negative. It goes negative, and then it approaches 0. Okay, so that's the behavior of the capacitor current. All right, so there is some difference between what we see in this driven case as far as V out is concerned and what we saw last time for the natural response. In the case of natural response, when we release the circuit with only a voltage on the capacitor, we saw that V out had a dip, right? V out would start from some value, go down and dip back. Whereas here, it's the current through the cap that has a dip, but V out and the inductor current, do not have that response. All right? Even for the overdamped situation. So that's something that we have to keep in mind. And as long as we intuitively understand what's going on, then that's sufficient, right? We don't have to worry about how the equations predict these. Of course, the equations should agree as well. Okay, so these were some qualitative looks at the behavior of the circuit in the case of overdamped response. And now, to find the exact overdamped response, we have to go back and ask ourselves how do we satisfy these conditions. So we say that S1 and S2 are known. We just have to find A1 and A2. So we say V out at time 0 plus is 0. That means that A1 plus A2 must be 0. Okay, so that makes sense. A1 and A2 are just opposite of each other. So that's fine. What else? Well, we also have to satisfy another condition that eventually is equivalent to this. Remember, we always have to rely on two initial conditions, one for the capacitor, one for the inductor. So last time we derived an equation for that. This time we should do the same thing. So we say at 0 plus, so at t 0 plus, what we have is this. I'm going to write the KCL at this node again, right? Remember last time we wrote the KCL? So what I have is I1 is coming in. So I1 is coming in. What's going out? We have C1 dV out over dt. So we have C1 dV out over dt. That's the current through the cap. We have no current through the inductor at 0 plus. Okay? And we have no current through the resistor. Why? Because this voltage is still 0. So remember, because this voltage is 0, all of the current has to flow through C1. So that's all we have. This is at 0 plus. So I can say that dV out over dt at 0 plus is equal to I1 over C1. I1 is the height of the step that we have applied, and C1 is the capacitor. Okay, so now based on these two, based on this equation, I can go ahead and take the derivative of this guy and satisfy it like that. So I can say A1 S1 plus A2 S2 is equal to I1 over C1. So here's one equation for A1 and A2, here's another, and that gives us the complete solution. All right, so does this solution agree with this general behavior that we predicted? Sure, why not? We have two exponentials in this response, right? We have two exponentials here. First of all, they have equal and opposite coefficients here. So at time 0, they sum up to 0. So that makes sense. At time infinity, what happens? At time infinity, because S1 and S2 are negative, both of these decay to 0. So yes, V out also decays to 0. So at least qualitatively speaking, with these two exponentials, we can create a waveform like this, right? It just depends on the values of A1 and A2 and S1 and S2. So this is the case of overdamped response for the parallel RLC tank while it's driven by a current step of height I1. All right? I will see you next time.